but in what context have you guys seen like functions and stuff like that? Feel free to share anything in the chat. I think that's really good if we can get some more ideas. Yep. Okay. So functions for graphs, definitely. So a lot of functions you can draw on a graph, and yes. Okay. I'd really highly encourage you guys to send messages to everyone, not just direct message, because like I'm seeing a lot of really good ideas, and it'd be super good if everyone shared them and everyone like knew about your ideas, because that'd be like really cool. Anyways, so yes, like I've gotten a few messages about, it's like function is basically inputs and outputs. So basically a function can be quite practically anything as long as you put in a single input and then it gives you a single unique output for your unique input. And that's basically how you can interpret what a function is. There isn't too much towards like the restrictions to functions, but we'll see that there are restrictions for different types of functions like polynomials. So now let's cover some terminology. So the values that you can put into the function is known as its domain. So the domain we usually use, well, at least in today's session, is going to be like real numbers. Sometimes the domain could be integers. It could be like natural numbers, which are like positive integers. And it just means that sometimes it's not that you can put any single number inside your function. So sometimes there's a restriction on the type of numbers you can put inside your function. And then your codomain is basically the same thing, but what you can get as your output. So it's the type of numbers you can get as your output. But the actual numbers you can get and you will get is going to be your range. And they might get a little bit confusing just to think about it like in terms of these words. But if you think about it as a graph, like we see below, the red section represents the domain of a function, right? So you can enter any number that exists in the red section into your function, and then it will give an output that exists in the blue, like in the blue section. However, the numbers you can actually get might be like a subset of the blue section, which is the yellow section. And the yellow section can be known as your range. Does anyone have any questions towards like how we define a function and what it really is? Okay, I'm gonna say that's no. Cool. And then we can just move on and let's talk about odd and even functions. So an even function is basically when you graph it, when you graph your function, it's symmetrical about the y-axis. Or if you think about it more algebraically, it basically means that fx, our function is f, and our input is x, right? So that's what fx stands for. An even function, if you put x inside your function, it gives the same output as if you put negative x, right? And that's how we define an even function. And an odd function, it's basically a function that if you graphed it, it has rotational symmetry about the origin. So if you rotate it 180 degrees around the origin, you get the same graph again. And that is algebraically, if you put x inside your function, is the equivalent to putting like the negative of putting negative x inside your function. So if we think about it a little bit more visually, there's a little picture on the right-hand side, and we can see that like y equals x squared is going to be an even function because we can see that it's symmetrical about the y-axis. And if you tried plugging in negative x into y equals x squared, you get x squared, right? And that's the same as if you put x in, you also get x squared. So that's an even function. And then if we think about an odd function, which is if I put negative x in, then I'm going to get the negative of if I put x in. And y equals x cubed has this property because if I put negative x in, I'm going to get negative x cubed. But if I put x in, I'm going to get x cubed, right? And then if I add a negative sign, they're going to be equivalent. So now let's try the problem where we prove that sine x is an odd function. Does anyone have any ideas towards how we could do this? I think there's quite a few ways you can think about it. So does anyone have any ideas towards how we want to do this? Okay, so I'm seeing some ideas about using SOHCAHTOA. Okay, I think that's not a bad idea. Okay. Right, okay. Yep, I think there's a lot of good ideas, but I think if we want to visually interpret it, I'll just draw it. Yeah, so I saw a really good idea of just graph it, right? Like if we can visually interpret it, that's kind of going to be a bit easier as well, right? So our usual sine graph just looks like this, right? I presume everyone's relatively familiar with the sine graph, right? So if you think about it, if we rotated this 180 degrees, so like we twisted this and here, we get the same graph, right? That's a visual interpretation of how we can think about it. Or if, let's say, y equals sine x, we know an even function should satisfy, oh, sorry, my bad, odd function should satisfy this, right? Um, so we basically want to prove that this is true. And yes, and this is quite obviously if we think about it like visually, right? Because we see that over here we have, if this is x sine x, negative sine x is over here. And this is negative x. Right. Does that make sense to everyone? Does everyone sort of understand like how even odd function should look like? Yes, no. Feel free just to say whatever you think. Because we can go, if we wanted to, we could also prove it for cosine, right? But it's a really similar process. And you could do it more rigorously if you actually wrote out the equation and you did like a little bit of manipulation to show that sine negative x is the equivalent to negative sine x. But then that's just a little bit more algebra involved. But as long as everyone understands how you can interpret it as like visually, yes, no, maybe, it's okay. Just say whatever you guys think. Okay, I'm gonna take that as a yes, and we'll move on. Okay. So now this is a bit more complicated. So now in functions, we have the concept of injective, surjective, and bijective. So what injective means is that it's also known as a one-to-one function, which means that for every possible output value in the codomain, like it has at most one only has one value in the domain. So that means that for every output we get, it has a unique input that gets it there. And how we can interpret this algebraically is that let's say we had a function where f(x) equals fy, right? Both of these should exist in the range of the function y, f. Right, and f is essentially our function. Now, if we think about it like this, an injective, if f is an injective function, it would have to mean x equals y. Because there's only one value that you can put into the function f that will give fx out. For example, if fx equals 2, the only input that we could possibly put might be like 4, right? So if like f4 equals 2, no other fy will equal 2 unless y equals 4. So it's basically saying that a unique input gives a unique output. Now let's move on to surjective. The surjective, it's a little bit different, and it means that for every value in its coda, there exists like it's also in the range. So it basically means that the codomain of the function is equivalent to the range of the function. So it means you can achieve all the numbers and all the values inside the codomain with the function f. So let's say our codomain was positive integers. Then basically what we mean that is that for any, let's say any value, let's say y in the codomain exists some fx equals y within the codomain with the function f. Let's move on to the last bit, which is bijective. Would mean that if every value in its range, like it's basically bijective is when a function is both surjective and injective. And that just kind of means it has to satisfy both that the codomain is equivalent to the range and that it's a one-to-one function, so that each output has a unique input, right? So this might be like a little bit confusing if you don't put it in context, but what we can do is we can think about like the function fx equals x. Okay, let's think about that. Fx equals x. Domain and codomain, right? And it's usually going to be written like something like this. So basically means that this part represents the domain, this part represents the code. So it just tells us what values we can have for the input and then what values we will get for our output. So this, in like this case, it just means that we can't get, if this was our the conditions we've been given, then it just means that we can't put any like imaginary or complex numbers within this function. Let's first prove that it's one-to-one or injective. Does anyone have any ideas towards how we could actually think about this? How could we prove that every output has a unique input? Any ideas? Yeah, so I've seen a response that like every input has its like own unique output, right? Like it's quite obvious because like this is basically a linear function, right? This is equivalent to y equals x. Okay. And what this means is that, let's say we had between, I think, a second. Okay, yeah. Let's say we had this. What we can do is, we know that fx equals x, right? And then we know, what would fy be equal to if we put y inside our function? Yeah, so I got a really good response from Jackie. It's equal to y, right? Because this is how our function is literally defined, right? So let's substitute this in to our original. What we get should be that x equals y, right? So this means that fx equals fy only achieved if x equals y. And this is enough to actually show that our function is injective. So usually this is like a really classic way to prove that a function is injective. Right. Okay. And now let's think about how to prove that it's surjective. Okay. So we know that our codomain is, let's say, like positive real numbers, right? Then let's say any value, let's say any a in, so a is just a random number that is a positive real number, right? How could we use this a to show that there exists like a function with an f with an input that results to a as the output? Well, what we can do is we say that f a equals a, right? And that's actually just enough to show that it's surjective. Because for any real positive number, as long as we put a inside our function, if our input is a, we're going to get a as an output, right? And then we've already shown that there does exist some input that satisfies this, right? And that's enough to show that it's both injective and surjective, which results in showing that it's bijective. Because by definition, any function that is both injective and surjective, it is bijective. Does everyone understand, like, have a good grasp on what these terms mean now? You don't have to be like 100% confident in how to use them in a problem. We just really want to introduce these concepts to you because it can come in really handy further on if you're looking at like functional equations and stuff like that. Does everyone just want to give me like a thumbs up if you understand, or if you don't, if you have any questions at all, just let me know in the chat. Okay. Sure. Okay. So what are some more examples of surjective? Yes. Oh, okay. Yeah, I know some of you guys have been to like April camp for the female and non-binary. So yes, we did have a lecture on something like this. So you probably have a bit more understanding, but no worries if you haven't ever heard of this, because like this is quite a complicated concept and like you don't hear about it a lot, especially not in like school math. But okay, so what are some other surjective functions? Any ideas? Well, a very, very classic one would just be this. What other ones can you think of? Can anyone think of? Let's say we're in like something like this. So real numbers to real numbers, right? We don't have to consider any other ideas to what some other surjective functions could be. Don't overthink this. This is like not a like trick question. You can think about like what you can think about like it as what functions are go really, really big and then go really, really small, but are continuous, right? Okay, I see a really good response of x equals x plus 1, right? You can think about like this is a line, right? I'm gonna tell you guys that like all linear functions are basically surjective for like real numbers to real numbers, right? Because the linear functions, they're continuous and they can go really, really small and really, really big. So like really, really negative and really, really positive. And they should cover all the real numbers, right? Because they go down and up infinitely. So there's always some input that will result in the output we want, an output that's now codomain. Yeah, so it can honestly be anything. It can be like 2x plus 4. Like all linear functions are going to be surjective. Okay, so a function can be both injective and surjective if it is if it satisfies the conditions that it's one-to-one and it's and all and its codomain is equivalent to its range, right? It's a bit confusing. What we can think about it is that like is it the part about surjective you don't understand that much, or is it more about injecting? Because we can go over them a little bit separately, and that might make it a little bit more clear because they definitely aren't the same thing. Okay, surjective. So surjective is when range equals codomain. And this can sort of mean that if we're given the codomain of like real numbers, it means that we can achieve all the real numbers, right? Not in all cases can you achieve all the numbers in your codomain, because if this was our domain, codomain, let's consider the function x squared. That's not going to be surjective, right? Because we can't achieve any of the negative numbers. X squared is always going to be like non-negative, right? So that means all the outputs are greater or equal to 0. But for our codomain, we were not told anything about like it being strictly greater or equal to 0. So that means we can't achieve any numbers or values in our codomain that are less than 0. And that's why it's not surjective. Yeah. So that's basically why something isn't surjective. And the exact opposite is when it is surjective. So if you can achieve all the numbers in its codomain. Yeah. Okay. Now let's move on to the next part. The next part is actually the main part of our course today. So we just want to show you like what functions are and how you can use them and some terminology that you see quite often associated with like functions. But now let's think about polynomials. So polynomials are a type of function, but not all like functions are going to be polynomials, right? Like it, let's say a function could be x to the power of half, and that's a function, but it's not a polynomial because a polynomial is defined as something that has coefficients and it's to the power of a like non-negative integer exponent, right? So we're really familiar with things like the linear polynomial because those are just linear lines. I'm sure you guys are familiar with the quadratic polynomial as well because that's like degree 2 polynomials, right? You'd see the highest power of x would be 2. So we refer to the degree of a polynomial as the highest power of x that exists within the polynomial, right? So that's basically the definition of a polynomial and how like when we use the word degree. So let's have a look at the polynomial below. So it says px equals x to the power of 4 plus 2x to the power of 3 plus 3. What would the degree of px be? Any ideas? Okay. Okay. Yes, I'm seeing some really good responses, and the answer is 4 because if we think about it, the highest power of x within this function or this polynomial is 4, right? There's no greater exponent. So the highest exponent is 4, and that would give us our degree. Right? Is that how everyone kind of thought about it and trying to see what the degree would be? Yeah, okay. I think it's just like terminology we use. Yeah. Okay, so then let's talk about roots of polynomials. So roots of a polynomial are quite important in a lot of cases, and it's basically defined as the values of x or our unknown variable, which for the polynomial equates to 0, right? So it can also, finding the roots of a polynomial is also sometimes referred to as like solving the polynomial. Is everyone familiar with like roots? Has everyone come across like roots of polynomials and solving for roots? Yes. Okay. Cool, cool, cool. Yeah. So that's basically, I think everyone's going to be quite familiar with that. And now let's move on to a very important result that we have in algebra, and that's known as the fundamental theorem of algebra. How many of you guys have heard of something like this? Like, even if you don't really know what it talks about, have you like guys heard of it? No worries if you haven't. Okay, that's fine. Basically, what it means is for a polynomial of degree like d or whatever its degree is, it has at okay. This is not okay. So for polynomial with degree d, it has at most d real roots. Or if you think about it as, it really should say like the same degree, but anyways, if it has degree n, it means you have at most n real roots, and it can possibly have less than n roots because some roots might be complex. And you don't have to think about that too much. You just have to remember that for any polynomial of the highest degree, like whatever its highest degree is, it has at most that many real roots. So if we're thinking about quadratics, how many roots can you possibly, like at most, have for a quadratic in terms of real roots? Yeah, really good. 2, right? Because the highest power in a quadratic is 2. What about cubes? What about cubic polynomials? Yes, exactly, right? Dude, like I said again, you guys are giving like full, really correct responses and really good responses. It'd be super good if you guys like shared it in the main chat because like then everyone like can interact with each other a little bit more. So okay, I'll ask one more. What about like a quintic polynomial? Or okay, or like um, no. Is it because like not everyone's sure like what degree quintic has? I just have some internet. Give me a second. Okay. Okay. Sorry. Yes. Hello? Can everyone hear me? Just to make sure. Yes. Yeah. So quintic means like a fifth degree polynomial. So at most, by the fundamental theorem of algebra, it's gonna have like five real roots, right? You can't have more. And an extra for experts is to prove the fundamental theorem of algebra. I think you can do this with like contradiction, proof by contradiction, or other ways. But it's definitely a challenge. So if anyone's like up for that, definitely consider why this is the case and how like the fundamental theorem of algebra might have come like about. But okay, does everyone sort of understand what the fundamental theorem of algebra is stating? Yeah. Okay. So why we really introduce this is that it can become quite useful in questions that might ask us to find all the real roots or all the roots of a certain polynomial because it gives us an upper bound, right? So we're not just continuously searching for roots. We know that, okay, well, it has a maximum of this many roots, right? So after you've found a certain number of roots, like say you've already found n real roots for an n degree polynomial, you know that there's no more other roots, right? And then you can just end the question there. So that's when it can become quite useful. And other than that, it can also be useful in other cases, but you'll know when you can use it. Okay, so a very important part of our lecture today is also about Vieta's formula. Okay, I'm just gonna ask, how many of you guys have heard of Vieta's formula or used it even? Because not necessarily has everyone seen it. But you might be a little bit familiar with it in terms of for like quadratics. Okay, yeah. So somebody's thought like used it for NZMO round one Q8. That's really cool. If you used it before, that'd be amazing. Okay, so basically, it's a really useful condition that tells us about the relationship between the roots of a polynomial, right? So when a polynomial has a really high degree, sometimes it becomes so really hard to calculate what the value of its roots. And what the Vieta's formula can like help us with is it shows us a relationship. It doesn't necessarily tell us what these their certain roots are, but it can tell us what the sum of the roots are, or like what are the pairwise by times uh, every two roots together, like and then added them together, what value do I get, right? And that's why it becomes really useful. So then let's look at the formula below. It can be quite confusing if we just look at that, but what we can do is we can think about it a little more clearly. Okay. Does everyone have the handout that we sent with like beside them, or have it as a reference, or even just had a look at it yet? No? Has everyone seen the handout? Because it does go a bit more in detail inside the handout, so it might be really handy if you do have the handout with you. Okay, so I see some people do have the handout with them, but no worries if you don't. If you want to refer to it like after class as well, that could be really useful. Okay, so let's say our polynomial, just not to confuse you guys with like functions and polynomials, let's say it's px, right? So this is our polynomial. What the Beatrice formula states is below. So let's say the roots of px are r1, r2, r3, all the way to rn, right? And it's an n degree polynomial. Notice that when we say r1 all the way to rn, it doesn't necessarily mean that all these roots are real. They could be complex, or they could be like something that's really confusing. We don't really care about it. We just care about the relationship between them. We don't care about their individual values, right? So what Vita's formula tells us is the relationship between the roots. So if we think about the first one, which is, I'd say, the most handy one and the most easy to understand one, is that if we sum all these roots together, it should be equal to the coefficient of this coefficient, and this coefficient. So it should be the coefficient of x to the power of n minus 1 divided by the coefficient of x to the power of n, right? So that's what all these like a's and r's stand for. And basically it tells us a lot about the relationship between all these functions, all these roots, because it tells us now that if I paired every single root with another root, not including itself, so like we can't have r1 with r1, we can pair r1 with r2, and then r1 with r3, all the way until r1 with rn, and then we're going to pair r2 with r3, r2 with r4, all the way until r2 with rn. And we did this for all the roots, and we then added them together. It again shows us relationship that it should be equal to the coefficient of x to the power of n minus 2 over the coefficient of x to the power of n. Right. So mainly I'd say the most useful parts of Vita's formula are going to be like the first one, the second one, and potentially like the last one, where it tells us the product of all the roots together is equal to -1 to the power of n a0 over an. That just means the constant value over the coefficient of x to the power of n times -1 to the power of n. So that means that if n, the degree of p, is odd, then -1 to the power of n is going to be odd, right? But if px is like something like a quadratic, then that's degree 2, and n is going to equal 2. So -1 to the power of 2 is going to be positive. And it shows us a relationship of whether it's going to be positive or whether it could potentially like be the negative of a0 over an. Does that make sense? So like what Vita's formula is stating, does that make sense to everyone? Okay, cool. So that's basically what it means. Like it's really fussy about like how much like because there's a lot to it, right? There's a lot of variables, and then if you're not too sure about what a n minus 1 stands for or what like rn stands for, it can be really confusing. So just make sure that you understand all the variables inside Vita's formula, and then it can become really handy when you're attempting problems. So that's basically what the Vita's formula states. Now let's have a look at this first problem. So if I write it again, this. And I hope that like um everyone can share some ideas in the chat. And if anyone actually comes up with a solution, like I think that'd be amazing if you'd want to share it with everyone, just like to practice your skills on like how to present your solutions and how to make it understandable to other people as well. So we have our polynomial here, and what we basically want to show is, so it has the roots r1 and r2, right? We want to find the value of r1, 1 minus r2, 1 minus r2. Okay, I'm going to give everyone like a few minutes to attempt this, and then we'll go over it together. Okay, so if everyone just want to like take out a piece of paper or anything and just scribble on it and try to figure it out, that'd be really cool. Here, I'll just write out Vita's formula to give you guys a hand about like some parts that might be really useful. Referring back to what we had here, notice that it's this. And in this case, n equals 2, right? So whenever it's quadratic, n equals 2. So it should really just be negative a1 over a2, right? And then this should be okay. Does anyone have any ideas? Okay, I'll give you guys a few minutes. And if you have any ideas, like it'd be super cool if you want to share it. Okay, I'm already seeing like good responses. Let's see. Mm-hmm. Yes. So let's first figure out what the value of A2, A1, and A0 are going to be. Does anyone like have any ideas? So A1, I've seen a good response, should be negative 12, right? Because if we match them up with like, they're just the coefficients of these parts, right? So this with this with this, right? So that just tells us that A1 should be negative 12 and A2 should be, yep, 1. And what about A0? 19, yeah, okay, really good. So notice A0 is actually the value of the constant. So it should be paired with this, right? So these should match up like that. Just to make sure like you don't get it the wrong way around. It's A0 usually will refer to the constant value, whereas AN is going to be the coefficient of x to the power of n. Yeah. Okay, so now we've found all the values that we could possibly like use in Vita's formula. Does anyone have any ideas about how we can approach the rest of the question? If somebody wants to present their solution, that'd be like amazing. And I think that'd be a really good experience. Be brave. It's okay if you make a mistake. I think everyone just makes a mistake and then learns from their mistake. Okay. Um, uh, no pressure, but Jackie, would you like to share what you've said? because you gave a really good response, and I think it should be very, very helpful in solving the problem that we have here.
Well, I guess you just put like the A1 and the A2 into the equation itself, like carried it in.
Yep. And
So it'd be
you need something like
negative.
this.
Yeah.
Okay, cool. Right. Okay, that's really good. So what do you have any ideas on to like what we can do next? How can we approach this afterwards? Because this still looks a little bit different to what we want to achieve, right? Because we want to achieve the value of this. Okay, let's take a little sidetrack and let's expand this value, right? What should that be? That should be, right. Is everyone familiar with this? Like, does that, I think everyone should be good with that. Well, we can write this as, right? Yeah, okay. And what does this part look like? Does that look like something we already have? Yeah. Okay. Well, we can substitute that in for 12. Right, so that's not too confusing. And yes, okay. Again, Jackie has a really good idea. Do you want to share?
Okay, well, after the first part, for the second part, I was thinking maybe square the R1 plus R2, so that would be R1 squared plus 2R1 R2 plus R2 squared. And then you subtract 2 of the R1 R2 that we got from the
Yeah.
second equation. And
Yeah,
yeah.
and that's a really good idea, right? And we can find the value of what this is, right? Because we have the value of R1 plus R2, and we have the value of R1 times R2, right? So we just basically want to substitute this in. So it should be like 12 squared minus 219, right? Is everyone following along? Does everyone understand how this sort of part should work? Let me know if there's any part you don't really get, or okay, that's fine if nobody has any questions, or if you have questions a little bit later, just you can ask me as well. Okay, now this is a little bit of an extra for experts. There's the rational root theorem. And what it states is that we're only considering integer polynomials. So what an integer polynomial is, it's like any other normal polynomial except all its coefficients have to be integers, right? And let's consider an integer polynomial of degree n. What basically means that the coefficients a n minus 1, all the way down to a0 are all integers. And what it tells us is that if all the rational roots of this polynomial have to be of the form like negative or positive r over s, where r is a factor of a0 and s is a factor of an. Right? So it means that if in our polynomial, if it has a rational root of a half, it basically means that 1 has to divide into a0, and 2, which in this case like represents the s bit, has to be a factor of an. Right. So that's basically what it states as a theorem, but also notice that not necessarily all its roots of the polynomial are going to be rational, right? There might be some like irrational roots, and we can't conclude anything about it from here. We can only make a conclusion about rational roots, right? And what the form of rational roots must take. It just means that its numerator has to be a factor of the constant value in the polynomial, and the denominator of the root has to be a factor of the coefficient of x to the power n. Does everyone sort of like understand what it's trying to say? Then let's try the problem of find all the possible rational, it says rational zeros, but that really just means like rational roots of the function fx equals 3x cubed minus 5x squared plus 4x plus 2. Let's try this question. And we only want to find the rational roots, right? So we don't care if it has the rational roots. We don't care if it's complex roots. We just want to find what are the possibilities that it could possibly have for this like polynomial down here. Okay, so I've seen some good responses, but I don't think it's all of the possible roots. So think about like all the factors of 2, right? And then all the factors of 3. So let's think about that for a little bit. Okay, so I've seen a really good response from Isabel. Isabel, do you wanna share your ideas? No pressure.
So like A0 and AN are both prime. So you can just substitute in all of the divisors in it in the R over S thing.
Yeah, so I think yes, yeah, you're definitely on the right track. So let's consider the factors of A0, right? And in this case, what is A0? What is A0 in our case for the polynomial? Well, it's equal to 2, right? So we basically want the factors of 2. What are the factors of 2? I think everyone is pretty familiar with the factors of 2. Yep, this was 2 and 1. Right, and we can really include like positive and negative, but let's just say think about positives. 2 and 1. Then what are the factors of, or first, what is the value of an? What is the value of an? So the highest degree in our polynomial. Right, so it should be 3, right? Because 3 is the coefficient of the highest power we have in our polynomial. And that is basically our an. So factors of 3 should be 3 and 1, right? So let's pair them up randomly. Well, we want to pair one factor of 2 with one factor of 3, right? Because we want to pair one factor of A0 with one factor of AN. And that can be 2 over 3, right? And that can be 1 over 3. And then that could be 2 over 1 and 1 over 1, right? And we have to notice that it's plus minus, right? So it can also be negative 2 over 3, negative 1 over 3, negative 1 over 1, or negative 2 over 1, right? So I've typed into the chat, so if everyone wants to have a little bit look at that. And it doesn't necessarily mean that all these numbers are gonna be roots of our polynomial, but it shows all the possibilities. And that's a lot easier than checking every single number we know, right? Like if we were trying to find roots by just guessing, this narrows down our guesses by a lot, because that means we don't have to consider like other random rational roots, such as like let's say 4 over 5, because we know it's not going to be a rational root of our polynomial by the rational root there. So that just limits the number of actual inputs we have to try for x to see if we get 0, right? And actually narrows it down by a lot. And that's why it can be sometimes really useful when we're using the rational root thing, because it tells us what are the possibilities that we can get and what are the ones that definitely just won't work. Does anyone have any ideas to like other questions or anything they want to add? I think this is a little bit of an extension, but it can also be really helpful if you are trying to search for roots, because when roots get like to a higher degree and it's a lot more complicated, sometimes the best way to actually find roots are just to substitute values in and see if you get 0 as your output, right? Because we want to equate the polynomial to 0 to find the root. And if it does, it means that we have found it. If it doesn't, then it just means that it's not a root of our polynomial. So